Okay, welcome everybody. This is the recording of our second lecture, Problem Solving Through Search. Now I'm re-recording it because I forgot to press the record button on Zoom, so I'll make this publicly available after I finish recording. So, in talking about problem solving through search, we first have to talk about the problem solving agent. So a problem solving agent is one kind of goal-based agent that uses atomic representations. And again, when we say atomic representation, we're talking about states of the world that are considered as a whole. So there's no internal structure visible to the problem-solving algorithm. And this is distinct from, say, a more structured or factored representation, which would be typically used by more advanced agents such as planning agents, which are a different type of goal-based agent. And we'll see these later in the course when we cover topics such as uh, planning and scheduling. Okay? So first off, I guess we have to say that problem solving begins with precise definitions of both the problem and the solution. And we're going to go through a few examples of these to illustrate the difference. Uh, we'll then go on to describe several general purpose search algorithms that can be used to solve these problems, mainly in the form of uninformed and informed search algorithms. Now, our uninformed search algorithms, they're those that are given no information about the problem other than the definition. And although these can solve any solvable problem, they rarely do so efficiently, while informed search algorithms can do pretty well as long as you give them some heuristics as to how to solve a problem, which we won't cover in today's lecture. We'll leave that off to next week. Um, an important limitation to keep in mind is that we are only considering the simplest kind of a task environment, so that the solution to our problem will be a fixed sequence of actions. So we won't consider any actions outside that sequence, and we won't take in additional percepts as we move through the sequence of actions, which I'll talk a little bit more about in a moment. So goal problem and our goal and problem formulation. In relation to goal formulation, goals help us organize our behavior by limiting the objectives that the agent is trying to achieve and the actions that we need to consider. So it's based on the current situation, and the agent's performance measure is the first step in identifying that problem solution. Problem formulation is the process of deciding what actions and states to consider given a particular goal. And we'll see an example of this. Okay, getting to Bucharest. This is a classic example where you consider yourself to be visiting Romania and you're in the city of Arad. Now, in trying to come up with a performance measure for our interaction with this world, you can consider a multitude of factors. You can consider the sites you want to see, what you want to do, how much you want to spend. So there are far too many factors or percepts to consider. So this results in a complex decision problem where there's a multitude of trade-offs and far too many for us to consider in terms of actually identifying a problem solution. So we abstract away from that and simplify it. And we do that by giving us a guiding goal. And our goal in this instance is that we have a ticket that flies out for a flight that leaves Bucharest on a subsequent day. So what that means is that we have to get to Bucharest within a day. So in that case, it makes sense for the agent to adopt the goal of getting to Bucharest. Now, adopting this goal enables us to disregard any courses of action that don't reach Bucharest in time for us making that flight. So the decision problem is greatly simplified by doing that. Now, the goal is a set of world states, particularly those states which result in the goal being satisfied. Our agent's task is to find out how to act, both now and in the future, such that we reach that goal state. Prior to doing this, though, we need to decide what sorts of actions and states we should consider in arriving at the goal. And this brings up the question as to what level of detail do you actually consider the actions. So again, if you make them too small, and it adds to the complexity of the problem, such as, do I turn left or right at a per meter basis, etc. Okay, so again, we want to abstract away from that problem. So we want to reduce the level of detail to reduce the uncertainty in the world and reduce the number of steps in forming a solution for the problem. So for now, what we're going to assume is that the agent will consider actions at the level of driving from one city to another. Okay, and each state will therefore correspond to being in a particular city. So now that the agent has the goal of driving to Bucharest and is considering where to go from Arid, our current location, we can see that there are 3 roads that lead out of Arid. Okay, so we can decide to go to Zarind, we can decide to go to Cebu or Timisoara. Okay, now carrying out any of these actions will not result in us achieving our goal. So unless the agent knows the actual layout of cities in Romania, then it won't know which road to follow. So as a consequence of that, the agent won't know which of the possible actions is the best action to take, because it doesn't know enough about the state that results from taking each action. And like this is okay. So to classify this problem, if we say that the agent has no additional information, the environment is unknown, and in that particular case, the agent will be forced to try one of the actions at random with the hope of arriving at the goal state. But for this problem, we're going to assume that the agent has a map of Romania and knows the roads that connect city to city, and as such the environment is known. So the agent can use this information to consider each subsequent state in formulating a hypothetical journey via all of the different cities. Now, that will enable it to find a path on the map from Arid to Bucharest, and it can achieve its goal by carrying out the driving actions required to get from one state to another. Typically, we say that an agent with several immediate options of unknown value can decide what to do first by examining future actions that eventually lead to states of a known value. Okay, so the environment. So because it's necessary to examine our future actions, we have to be more specific about our actual environment. So we say that our environment is observable, it's discrete, it's known, and it's deterministic. It's observable in that the agent always knows the current state. So as the agent drives from city to city, it's reasonable to assume that there is a sign indicating that you have arrived at the city. It's discrete in that when we arrive at any given state, there are only a finite number of states and actions to choose from. And again, this is true for navigating in Romania because each city is only connected to a small number of other cities. We say it's known because the agent knows which states are reached by each action. Having the map enables us to do this. And it's deterministic because we assume that each action has exactly one outcome. And again, I mean, this just means that if we leave Arid to go to Cebu, we end up in Cebu and not in Timisoara by accident. Okay? So the question we ask is, under these assumptions, the solution to any problem is a fixed sequence of actions. When is it not? Okay. Well, we would say that it's not when there is a branching strategy, or like we're picking our action as new percepts arrive. So, or it doesn't happen as expected, whereby we go to one city and we find out that there was a fault in the action, whereby we ended up in the incorrect city. Again, you can think back to your example of the vacuum environment, whereby the dirt sensor or the Hoover sensor is faulty and the actual result isn't what we expected. So in those cases, it may also be necessary to have a contingency plan to enable the agent to correct its actions such that it still achieves its goal state. Okay, so if the agent knows the initial state and the environment is non-deterministic, it knows exactly where it will be after the first action and what it will perceive. Since there's only one percept possible after the first action, the solution can specify only one possible second action, and so on. Now, this enables us to utilize search. So search is the process of looking for a sequence of actions that reaches the goal. The search algorithm takes the problem as input and returns a solution in the form of an action sequence. Once the solution is found, the actions it recommends can be carried out. So this is the execution phase. Okay? So once we've formulated our goal and our problem to solve, the agent will invoke this search procedure to solve it. And then we'll use that solution to guide our actions, doing whatever the solution recommends as the next thing to do, typically the first action of the sequence. Then we would remove that step from the sequence and go on to the next one, and so on. And once the solution has been executed, the agent will formulate a new goal. So we have a simple formulate, search, and execute design for the agent. Just one thing to note, that while the agent is executing the solution, it ignores its percepts, such that it won't deviate from that, because it knows in advance what the result of that action and state will be. Now, this is considered an eyes closed approach, whereby we're certain of what's going on. Now, it's also considered an open loop system because we're ignoring the percepts. Because ignoring the percepts breaks the loop between the agent and the environment. So if we have 5, 10, 15, 20 actions and resultant states in our sequence, irrespective of the percepts experienced while carrying out the execution of that sequence of actions, we're ignoring them. So we're kind of deviating from our prior definition of agent and environment. Okay. So here's our algorithm for this. Simple problem solving agent takes in a percept, returns an action, persistent, a sequence, an action sequence, initially empty, state, some description of the current world state, goal, initially null, and problem, a problem formulation. So initially we update the state by passing in our current state and our percept. If sequence is then empty, so if we have not formulated a goal as of yet, we pass the state to the formulate goal function. So that will be a case of we're passing in the fact that we're currently in Arid and we want to arrive at Bucharest, and the formulate goal function then would arrive at that. The problem then would invoke the formulate problem function, which takes in our state and our goal. And again, this would create the sequence of actual, or this would prepare us for deriving the sequence of actions we need to take. Then the sequence invokes the search function, which takes in the problem, which generates us a series of action state pairings, which our agent could execute to arrive at the goal state. If sequence equals failure, then return a null action. In such case, if no path could be identified for our to solve the problem, and then once that's formulated, we carry out the first action, and sequence is updated to remove the first action and is equivalent to the remainder of the sequence of actions, returning the action we do. Okay? And that will be invoked until we have arrived at our goal. Okay. So, a problem can be defined formally by 5 components. We have our initial state. So, the initial state for our agent in Romania could be described as inarid, as seen there. The actions, given state S, actions S returns a set of actions that can be executed in S. So again, if we take the example of inarid, our applicable actions are go Cebu, go to Misora, and go Zarind. So again, it's just a description of the possible actions available to the agent based on the current state. Our transition model results SA returns the state that results from doing action A in state S. For example, inarid goes Zarind equals in Zarind. So again, the transition model allows us to see what the consequence of carrying out a hypothetical action at a particular state would result in. And that's critical to us identifying a search path that would enable us to achieve our goal. State, space, and path. For example, the map of Romania has nodes or states and edges or actions. Okay. So in terms of again, each of the cities themselves are actually our nodes or states. The roads adjoining or connecting the cities are our edges, and they denote our actions because they denote us going between one city and another. The state space graph, each road with 2 driving actions. Again, this is denoted because there are 2 potential actions for any collection or any 2 cities, because you can drive to or from. And the path is a sequence of states connected by a sequence of actions. And again, these will be pairs of current state and the action taken. And okay, so again, together, if you're to take the initial state, actions, and the transition model, you're implicitly defining the state space of the problem. So that's the set of all reachable states from the initial state by any sequence of actions. So in this case, our state space is forming a directed network or graph, whereby nodes are the states and the links between the nodes are the actions. Yeah, okay. So the goal test itself, again, is as you're seeing, it's helping us determine whether or not a given state is a goal state. And again, this is formatted by the prior algorithm, format search execute, whereby we're passing in our current percept, which is our current state. In the case in Bucharest would be the example of the successful goal state in this example. Okay? And again, we can have an explicit set of possible goal states, and the test simply has to check whether the given state is one of them. So in this instance, we have one state that is our goal test in Bucharest. However, in other cases, you can have a goal could be specified by a more abstract property rather than an explicit set of enumerated states. So if you were to take the example of playing chess. Okay, the goal is to reach a state called checkmate. Now, under that goal, the opponent's king is required to be under attack and incapable of moving from its current location. Now, that's more abstract because the particulars of the current location of the king and your pieces are not specified. It's an abstract relationship between them. Okay. So path cost, the function that assigns a numeric cost to each path. So our problem-solving agent can choose a cost function that reflects its own performance measure. And again, in our example, the agent is trying to get to Bucharest. So we can assume that time is an important consideration. So the cost of a path might be its length in kilometers between cities, and then we denote the time it takes us to travel that in the remaining time. Step cost, we assume that the cost of a path can be described as the sum of the cost of the individual actions along the path. So again, when we're deriving the cost of arriving in our goal state in Bucharest from one of the potential successful sequences of actions we can take, it's the summation of the cost across that sequence of action. Okay, the step cost of taking action A in state S to reach state S is denoted by cost of the state, action state. The step costs for Romania are shown in Fig 3.2 as route distances. We assume that step costs are non-negative. And again, they're non-negative because that would result in a looping condition whereby we would always follow that path because it's reducing the overall cost of the sequence of actions we can take. A solution to a problem is an action sequence that leads from the initial state to a goal state. Solution quality is measured by the path cost function, and the optimal solution has the lowest path cost among all solutions. Again, there is a multitude of solutions in our examples, so the optimal solution is that which will have the lowest path cost of all those solutions. Okay. So in formulating problems, we propose the formulation of the problem of getting to Bucharest in terms of the initial state, actions, transition model, goal test, and path cost. Okay, so if we're to compare the simple state descriptions we've chosen in ARID to an actual trip across the country, where the state of the world includes a multitude of things. Again, getting into the minutiae of the detail. So like type of car you're traveling in, passengers, what you do on the way, weather conditions, stopping for food, etc. The problem becomes unbelievably complex because the world is difficult to model with that level of detail. So while it could seem a reasonable formulation, as it is a model, what we would like is a more abstract mathematical description as opposed to the real thing, because it avoids a number of the real world states that can cause us problems in deriving a solution. So any considerations that are considered irrelevant to the problem of finding a route to Bucharest are omitted, and the process of removing detail from this representation is called abstraction. So in addition to abstracting the state description, which is the city, we also have to abstract the actions themselves. Because, for instance, a driving action can have a multitude of effects, as well as changing the location of the vehicle. The people in the vehicle could change, the lane we're traveling in could change, the speed we go at could change, the fuel we could consume as a result could change. Our formulation is only taking into account the change in location. and there's a multitude of actions we omit altogether in relation to driving a car, because we don't want to specify a too small level of detail, which makes it complex to both model the world and model the impact our actions will have on that world. So, in relation to abstracting actions, can we be more precise about defining the appropriate level of abstraction? So if you think of the abstract states and actions we've chosen as corresponding to large sets of detailed world states and detailed action sequences. But now consider a solution to the abstract problem. Again, we'll take the example from the Pat Arid to Cebu to Ramanuka Vilcay to Bitsy to Bucharest. Okay? So that's a series of different actions and relevant states. But this abstract solution corresponds to a large number of more detailed paths. For example, if you drive with the radio on between Cebu and Rimku Valley, you could carry out any of these small little actions that would change the whole variation of the problem. So, while we can add more detail and finer grained actions, the abstract solution is still valid because we can expand from the abstract to incorporate finer grained levels of detail. So that would be a perfectly valid approach to take. And the abstraction simplifies the process of actually doing those actions, and that detail can be added at a later time, or for bespoke problems you actually want to solve, as opposed to just immersing us in so much detail that we lose track. Okay, so again, the problem-solving approach, it's being applied to a multitude of task environments. But what we're going to discuss now is a series of toy problems. So toy problems are typically used to illustrate a variety of problem-solving methods. They provide a concise, exact description, and they're usable by different researchers to compare the performance of their algorithms for realizing that problem-solving approach. This is differentiated to real-world problems, which are problems that typically we would care about the solution. In that instance, there very rarely is an agreed upon description representation for it, but you can get the general formulation of the problem. Compared with real-world problems, toy problems typically have, well, this instance of the problem, the vacuum world, would have discrete locations, discrete dirt, reliable cleaning, and it never gets any dirtier. So these are assumptions we can make about this toy problem for a vacuum world. Again, if you had a Roomba in the real world, the characteristics of the task environment would differ significantly. Okay, so again, we're familiar with the vacuum world. We have a two-tile world. We have dirt or no dirt in our tiles, and we have a Hoover in one tile. It has a series of actions it can perform, such as left, right, suck, no suck. It has a sensor for detecting dirt. So we'll just go through a few of the properties of this toy problem. The state is determined by both the agent location and the dirt location. The agent location is one of two locations, each which might or might not contain dirt. So thus there are 2 times 2 to the 2, which equals 8 possible world states. A larger environment with n locations has n times 2 to the n states. So we were debating this last night on the live lecture. because I was trying to think in my head how that would be realized for our example from lab 1, which was the farmer feed chicken and fox problem. So in that world we have only 2 locations. That's n times 2 to the n. So that would say that there's, again, it would be similar in that that would be 2 times 2 to the 2 different world states. Now, is that correct? Which it is correct, because we have 3 percepts at 2 to the 3. Yep, okay. So that is correct. So if you were to create every permutation of the perception of the fox, chicken, and the feed, then you should end up with 8 distinct states. Okay. So the initial state, any state can be designated as the initial state or actions. In the simple environment, each state is just 3 actions, left, right, and suck. Larger environments might also include up and down. So if you wanted to add additional actions by adding additional tiles to enable the capacity to move, of course that would also change the number of potential states in the world. Transition model, the actions have their expected effects, except that moving left in the leftmost square, moving right in the rightmost square, and sucking in a clean square have no effect. And again, this is a process of abstraction. So in your environment, agent program, and agent, you would have to handle what happens when you say move left and you're in the leftmost tile. But we're abstracting away from that in terms of trying to identify a search-based approach for solving the problem. Goal test. This checks whether all the squares are clean. And path cost. Each step costs 1, so the path cost is the number of steps in the path. Okay? Okay. A second toy problem, which is the 8 puzzle problem. Now, the 8 puzzle is an instance of a block puzzle as shown. It consists of a 3x3 grid with 8 numbered tiles and a blank space. Now, a tile adjacent to the blank space can slide into the space, so you're able to move the tile into the blank space. So if I was to move 1 over there, it would result in 1 now being present here, and this now being a blank space, and so on. The objective is to reach a specified goal state, such as the one shown, which is typically going from an unordered to a ordered representation. But again, you can configure that whatever way you want. So our states, the state description specifies the location of each of the 8 tiles and the blank in one of the 9 squares. The initial state, any state can be designated as the initial state. Note that any given goal can be reached from exactly half of the possible states. Actions, the simplest formulation defining the actions as movements of the blank space, left, right, up or down. Different subsets of these are possible depending on where the blank is. So again, if the blank is present on the rightmost, then there's only a subset of the actions will be available to you. Okay? Whereby if the blank is here, for instance, well, let's say if the blank is here, we can't move the tile 3 down. We have to move it up. So only a subset of actions are available. Goal test, this checks whether the state matches the goal configuration, shown on the right hand side, and again we can specify whatever configuration we so wish. And again, each step costs 1. So there are a number of abstractions included here. Okay, the actions are abstracted to their beginning and final stages, ignoring intermediate locations where the block is sliding. We've also abstracted away any actions such as shaking the board when pieces get stuck, and we're ignoring any physical manipulation such as extracting the pieces with a knife and putting them back in again. Okay, and they are all considered abstractions. So then we're left with a description of the rules of the puzzle, avoiding all the details of physical manipulation. Now the puzzle itself, it belongs to the family of sliding block puzzles, and these are often used as test problems for new search algorithms in artificial intelligence. And the problem is known to be NP complete, so we don't expect to find methods significantly better than the worst case. Then the search algorithms will describe in this week and next. Okay? And just to give you a flavor of the complexity of the problem. Okay, if you can ignore those. So the A puzzle has 9 factorial divided by 2, and it's divided by 2 again because we can reach any potential state from half of the possible initial states. So it's quite easily solved because it's only 180,000 different states. But when this goes up to 15 puzzle on a 4x4 board, it results in 1.3 trillion states. But again, random instances of the problem can be solved optimally in a few milliseconds by the best search algorithms. Then we go to 24 puzzle on a 5x5 board, which is about 10 to 25 states, and random instances can take several hours to solve optimally. Okay, and if we go to a 6x6 board, it becomes even more massive as a problem, and suddenly you're into days, months, or years and to actually derive a solution. So you see quickly that deriving all the permutations of state action sequences in terms of being able to find a successful path state becomes intractable very quickly. Okay? So another problem is the A queens problem. So the goal of the A queens problem is to place A queens on a chessboard such that no queen can attack any other queen. And again, you should know your rules of chess. A queen can attack vertically or horizontally or diagonally, okay, in both directions. So where you see an attempted solution here which is failing, and it's failing because the queen here in the leftmost column is being attacked by this queen down here in the rightmost column, or vice versa. And although there are very efficient special purpose algorithms for this problem and for all the n-queen family of these problems, it's still a useful test for search algorithms. Okay, which I'll talk about in a moment. First, let's go through the different environment information. So the states, any arrangement of 0 to A queens on the board is a state. So you have to place 8 queens on a board. The initial state is that no queens are on the board. Our action is we can add a queen to the board. The transition model returns the board with a queen added to the specified square. The goal test, 8 queens are on the board, none are attacked. So again, this is a more abstract representation of a goal state because we're not taking into account the particular location of each of the queens, assuming that we're adhering to the rules as set out by the goal state. Okay. So, and the number of databases in which this is 1.8 times 10 to the 14 are the possible sequences we can investigate. So a better formulation will prohibit placing a queen in any square that is already attacked. Okay. So, and this, there's two common ways to solving this problem. Okay. You have incremental formulation and you have complete state formulation. Okay. So, incremental formulation, this is where we specify a set of operators that augment the state description, where we start with a empty state for the A queens problem, such that each action adds queen to state. Okay, so our state definition has changed to state that all possible arrangements of n queens, one per column in the leftmost n columns with no queen attacking another. So we start off the leftmost, then we can't put one here, and we can't put one here because that's the next leftmost. And we go, oh, we can here. Then we go here, then we go here. So on and so forth. Okay? So we go up and we consider these, and we can't go there, but we can go here. And so forth. And this would be a valid goal if our queen was placed here. Okay. So adopting this formulation reduces the A queen state space from 1 to the 8, 1.8 times 10 to the 14 to just over 2000. And solutions are relatively easy to find. Okay. The complete state formulation, which is the second approach, starts with all the A queens on the board initially. Okay. Which is like the initial one we specified. And then we have to produce permutations of their positioning in order to try and identify a suitable goal state. Okay? But that won't, that results in a very, very laborious manner of actually trying to drive a solution, because you're going to hit multiple, put a queen here, then you put a queen here, and you say, oh, fail, try again, and so on and so forth. So by changing the state formulation, then we're actually improving our tractability of the problem. Okay? I hope that makes sense. Okay. So another real world problem, or our first real world problem we'll consider is travel planning. Again, each state will include a location and an airport and the current time. The cost of the action can be defined as the flights we intend on taking, how much it costs, where we're traveling to, is it in one country or multiple countries, and any other additional information we want to add. The initial state is specified by the user's query, traditionally just where you're flying from, where you're flying to, and where you're flying from, and the current date and time. And the actions you want to take are where you're flying or where you want to fly to, the seat you want, the time you want to leave, etc. Transition model, state resulting from taking a flight, will have the flight's destination as the current location and the flight's arrival as the current time. Our goal test, have we arrived at the destination specified? And the path cost can depend on a variety of factors depending on what you include. So it could be the monetary cost, the waiting time, flight time, customs and immigration procedures, first class, second class, do you mind having a long wait over, and so on. Now, We've already seen an example of this problem in the terms of root finding in our map of Romania. But there are like a multitude of things that these could consider. Some of them do, some of them don't. Okay? So like in building a root finding algorithm, you want to provide, you always want to provide for when things can go wrong. So contingencies is an important element of it. Okay? So what could go wrong if a flight's delayed? You know, what's the likelihood of a flight being delayed? Are you being charged unfairly? Is there an additional charge for moving in bags? What are the seasonal constraints to do with flying? Okay, so if we had a grade system, what it would do is take into consideration all of these contingencies and build a solution that enables you to address them. Okay, and real world problems, very large scale integration, VLSI layout. So a VLSI layout problem requires positioning millions of components and connections on a chip to minimize area, minimize circuit delays, minimize stray capacitances, and maximize manufacturing yield. Okay, so typically I just think about Intel and their fab up in Kildare producing the next set of compute chips, okay, and microprocessors. They want to squeeze as many circuits they can onto a smaller and smaller chip in order to increase compute and decrease the cost of the chip. So this introduces a layout problem, which comes after the logical design phase, and it's typically split into two parts: cell layout and channel routing. So in cell layout, the primitive components of the circuit are grouped into cells, each of which performs some recognized function. Each cell has a fixed footprint, so a size and a shape, and requires a certain number of connections to each of the other cells. The aim is to take the cells on the chip so they do not overlap, and so there's room for the connecting wires to be placed between the cells. Then channel routing is used to find a specific route for each wire through the gaps between the cells. Now, it's a very complex problem, but it's definitely worth solving. It's worth solving because it increases the compute of the chip, makes them cheaper to produce, and it's a sought after skill. So I had looked for VLSI jobs on Glassdoor. While I didn't find any, what I did find was very related to it, and that's ASIC chip design. So ASIC chip design is application specific integrated circuits, okay, which is very similar. So again, if you think of the Intels and the AMDs of the world as the state of the art, they have the whatever generation fab they're on, they can produce the smallest silicon chips and get as many circuits on it as possible. But like ASIC is kind of more customized chip design for particular purposes. So think of jobs like designing specific chips for your camera or a webcam or for Bitcoin mining or for anything to do with FPGA design, etc. You know, and this is becoming more and more common because you have compute-heavy tasks which hardware chips are able to solve much faster than the abstracted software-based solution for doing so. So manufacturers are integrating ASIC chips into their devices, and they can be anything from a smartphone to a digital camera to increase the compute of that device. Okay? And that doesn't need state-of-the-art fabs. So if you take, for instance, Tyndall in University College Cork, they have a fab that can produce chips down to a specific nanometer. I can't remember the specifics of it again, but they would regularly collaborate with industry in the designing of chips for specific industry purposes. Now, being able to identify a problem solution that can be searched for that layout is a valuable skill to have, and there are roles available currently in Ireland for ASIC chip designers. So it's something to keep an eye on if it's an area you're interested in. Okay, so now having formulated our problems, we now need to solve them. So our solution is an action sequence. So search algorithms work by considering various possible action sequences. The possible action sequences starting at the initial state form a search tree with the initial state at the root. That's this guy. The branches are actions and the nodes correspond to states in the state space of the problem. So each of these branches refers to an action. Again, for our example, it would be go Zabu, go Timisoara, go Zarand. And when we carry out that action, we would see that this node has been expanded. Okay? So this figure is showing us the first few steps in growing the search tree, starting with the initial state in Arid in an attempt to find our route to Bucharest. Okay? So the first step is to test whether this guy is our goal state. So is in Arid our goal state? It's not. So then we need to consider what actions we can take. We do this by expanding Arid, which is why this is highlighted in a dark gray. Okay? Then we can look at applying any of our legal actions, which will generate a new set of states, and we add 3 branches. So being in Cebu, in Timisoara, and in Zarind. So each of them are legal actions. And then we choose which of these 3 possible actions to consider further. Now in this case we consider in Cebu. Okay? And this is basically the essence of search, or search in a nutshell. Okay? Now we're opening up one option and putting the rest aside for later. If the first choice doesn't lead to the solution we desired, then we check to see if it's in a goal state or not. If it's not, then we revert back to the other ones. Okay? So, just on some of the terminology, each of these guys down here, the little white nodes, are called leaf nodes. What that means is at present, they are nodes in the tree that have no children. Okay? The set of all leaf nodes at any given point is called the frontier. Okay? The process of expanding nodes on the frontier will continue until either a solution is found or there are no more states to expand. And again, so like in this example up here, Arid is currently the frontier node. We expand it. Thereafter, these 3 nodes are added to the frontier. We expand Cebu. Thereafter, these 4 leaf nodes are added to these 2 leaf nodes combined together, which is the set of the frontier. Okay? So, our general tree search algorithm, we're going to show it informally here. So with our search strategy, how do we choose which state to expand? We have a possible action sequence starting initial state, with the initial state at the root. Branches are actions, nodes correspond to states in the space of the problem. So we have 2 different implementations here. We have tree search and we have graph search. We'll talk about graph search in a moment. We'll just focus on tree search right now. So tree search takes in our problem definition and it will return a solution or failure. It initializes the frontier using the initial state of the problem. So again, like our prior example, that would initially be the root node. Then loop do If the frontier is empty, then return failure. In this case, it's not empty because arid is in the frontier. So choose a leaf node and remove it from the frontier. So we choose arid, we remove it from the frontier. If the node contains a gold state, then return the corresponding solution. Arid is not a gold state, so we do not return a solution. Expand the chosen node, adding the resulting nodes to the frontier. So we expand arid, which results in 3 new branches being generated, which gives us access to Zebu, Timisoara, and Zurind. These 3 are added to the frontier, and then the loop continues because the frontier is not empty again, and it goes so on and so forth. Okay? So, okay, now, and that's pretty much the basis for most of our search problems. Okay? But one thing we have to consider is loopy paths, or redundant paths. Loopy paths are instances of redundant paths. So if we look at our search tree, we see that it includes the route from arid to Cebu and back to arid again. So if we see it down here, okay? So in that case, at this point, in arid is a repeated state in the search tree, and it's generated by a loopy path in this case. So if we consider loopy paths means that the complete search tree for Romania will be infinite because there's no limit to how many times we can traverse the loop, then we have to acknowledge that this can cause problems with the state space in that the original app only had 20 states, but now we have this infinite loop whereby we can keep expanding arid, okay? And loops can cause certain algorithms to fail, and it can make otherwise solvable problems unsolvable. But we don't need to consider it really, okay? Or we don't need to consider loopy paths. And there's a rationale for this. Because the path costs, so that's the cost of taking out the action going from Cebu to arid, is additive and non-negative, a loopy path to any given state will never be better than the same path with the loop removed. So eventually the cost will differentiate it as a goal state. Okay? So consider the paths arid to Cebu. So arid to Cebu is 140, and arid Zurind Ordea Zebu. Okay, 297. So we have 2 paths under consideration. Okay, one longer than the other. Now, because the second one is longer, we consider it redundant. It's a worse way to get to the same state. If we're concerned about reaching our goal, then we don't need to keep more than one path to any particular state, because any goal state that is reachable by extending one path is also reachable by extending the other. Again, ideally, we'll be able to define the problem such that we can eliminate redundant paths. But then in other cases, redundant paths are unavoidable, typically where the actions are reversible. So move finding problems and the sliding block puzzles would both be instances of problems that would experience that. Okay? So now if I go on to the next slide. Rectangular grid. Okay. So route finding on a rectangular grid is a particularly important example in computer games. In such grid, each state has 4 successors. So a search tree of depth D that includes repeated states has 4 to the D leaves, but there are only about 2D to the power 2 distinct states within D steps of any given state. Okay. So what they're saying here is that in this grid, So this guy, depending on the depth, we'll have a number of repeated states which will be exponential. Okay, but there's a far smaller number of distinct states within the number of steps taken for arriving at that state. So it can reduce the tractability of the problem by maintaining that and reducing what we consider. This leads on to the tenet that algorithms that forget their history are doomed to repeat it. So if we're to keep considering redundant paths, we are repeating it. So we avoid exploring redundant paths by remembering where we've been previously. And this brings us back to our graph search algorithm, which was a couple of slides back. Okay, and all this is there's very little differentiation between tree search and graph search. It's a graph search algorithm is simply the tree search algorithm with a data structure containing the explored set of nodes. So that remembers every expanded node previously. So when we go to generate a new node and it matches a previously generated node, one in the explored set on the frontier, it can be discarded instead of being added to the frontier because we've already arrived at it. Okay, so we'll just go through that there. So you see, it takes in a problem definition, just like the tree search. Initialize the frontier set using initial stated problem, so same thing. Okay, our problem will be we're currently in arid. The frontier would contain arid because it hasn't been expanded. Initialize the explored set to be empty. Loop do, if the frontier is empty, return failure. It's not empty, we have arid. We choose arid as the leaf node, remove from the frontier. If the node contains a goal state, then return the corresponding solution. It doesn't. Add the node to the explored set. Arid is added to the explored set. Expand the chosen node, adding the resulting nodes to the frontier, only if not in the frontier or explored set. So if arid is not in the frontier or explored set, then added. So that's grand. What would happen then? So we were in arid, then we get on to Cebu eventually, and then from Cebu we come back to arid again with our loopy path. But this arid would get down as far as here, when we go to try and expand it, and we would say that, oh look, arid is in the explored set, so discard and do not expand again. Therefore, we prevent the loopy path from reoccurring. Okay? Okay, so another nice property is that the frontier separates the state space graph into an explored region and an unexplored region, so that every path from the initial state to an unexplored state has to pass through a state in the frontier. Okay? So in that way, as each step moves from a state from the frontier into the explored region, while moving from a state in the unexplored region, you can see that the algorithm it'll systematically examine the states in the state space one by one until it finds a solution. Okay? Which is a benefit. Okay? So again, the search tree consistent with the graph search contains at most one copy of each state, so we can think of this growing tree directly as the state graph as shown. So again, you can see up here how it's like a growing tree. And you can see how it enables us to ignore taking particular actions because both the nodes were already in the frontier or the explored set prior to this action being prompted. Okay? Very good. Okay, so infrastructure for search algorithms. So search algorithms require a data structure to keep track of the search tree that is being constructed. For each node n of the tree, we have a structure that contains 4 components. State, the state in the state space to which the node corresponds. Parent, the node in the search tree that generated this node. Action, the action that was applied to the parent to generate the node. Path cost, the cost traditionally denoted by g of n of the path from the initial state to the node as indicated by the parent pointers. And we'll explore those in a little more detail. So we can see the visual representation of this relationship. So it's a parent-child relationship. Each node has a parent. Okay. We have an action denoted as right, and the path cost is denoted as 6. And our state is the current where we are at present. Okay. And then subsequent nodes can be derived as children of this parent that will themselves contain the action which resulted in that state being arrived at and the path cost associated with it. Okay, so function child node takes a parent node and an action and returns the resulting child node. Distinguishing between nodes and states, a node is a bookkeeping data structure used to represent the search tree. A state corresponds to the configuration of the world. Now that we have nodes, we need somewhere to put them. Queues. Okay. So let's look at the function. Child node takes in problem, parent, action, returns a node. Okay. Return a node with state, problem, result state, parent.state, and action. And again, our environment is known, the word is deterministic. So we can say what the result will be of taking this action given our current state, which is derived from the parent. Parent equals parent, action equals action. Okay, that's all fine. And then path cost equals parent dot path cost plus parent step cost for parent dot state for that action. So what is the cost of taking that particular action based on the parent's current state? And sum that with the prior cost of the parent. Okay? And in that way, we can maintain a sequence of actions and costs associated with those actions and states as we traverse through our tree, our search problem. Okay? So, notice how the parent pointers string the nodes together into the tree structure, so they're inherent in it. These pointers also allow the solution path to be extracted when a goal node is found. We use the solution function to return the sequence of actions obtained by the following parent pointers back to the root. So when we're in the goal state, we can simply ask what was the parent of each subsequent node in the sequence actions until we arrive at the root node, which gives us the sequence action to arrive at that goal state. So nodes on particular paths, as defined by parent pointers, where states are not. Furthermore, two different nodes can contain the same world state if that state is generated via two different search paths. So the state is separate to the actual node themselves, and we can have multiple paths that result in the same state occurring in the world. Now that we have nodes, we need somewhere to put them. The frontier needs to be stored in such a way that the search algorithm can easily choose the next node to expand. Queue. Okay, we use a queue for this according to its preferred strategy. The appropriate data structure for this is a queue. Okay, and we'll go through the different operations of the queue and what we can actually do here now. Okay, so operations of our queue. So again, our queue is our data structure for storing our frontier. The operations we perform is empty queue, returns true only if there are no more elements in the queue. Pop queue removes the first element of the queue and returns it. And insert element comma queue inserts an element and returns the resulting queue. There are three common variants we're going to discuss. That is last in, first out, or LIFO, first in, first out, or FIFO, and the priority queue. Okay? If you have a background in software development, you should have been exposed to these previously. Okay? So the FIFO queue. This pops the oldest element of the queue. So when we add to the actual FIFO queue, it goes to the back. When we pop, it returns the oldest. That's why it's called first in, first out. LIFO, or last in, first out, when we add to the, or insert to the LIFO queue, it's like we're stacking on top of the prior elements within the queue. When we pop, it's the last element that's being added that's being returned. This is analogous to a stack, which is a common data structure used in computer science, and I'm sure you're familiar with it. A priority queue. Now, the priority queue pops the element of the queue based on the highest priority according to some ordering function. And this ordering function typically is specified by you. Okay? So if we see here, if we're inserting nodes, and we're saying that it has a priority of 2 based on whatever the ordering function is, it will get inserted after the nodes with priority 1 and before the nodes with priority 3. Similarly, if we insert a node with priority 4, it will get inserted after the node with priority 4 and before the nodes with priority 8. And if we pop it, we will pop the node with the highest priority. Okay? Now, an explored set can typically be implemented with a hash table. And this allows kind of efficient checking for repeated states. And if you implement this well, the insertion and the lookup can be done in roughly constant time. And that's irrespective of how many states are being stored. Now, when you're implementing the hash table, be careful to implement the correct notion of equality between states. Okay? A common example you'll come across in a few weeks probably is the traveling salesman problem in meta-heuristics. And you may need a representation like this. But if you take the example of our 3 cities here, Bucharest, Urzikini, and Valsi, or Vasili, is equivalent logically to Urzikini, Vasili, and Bucharest. As such, the ordering of experiencing these states does not matter. Okay? And that's considered to be a data structure that facilitates that is considered to be in a canonical form. Okay? And that enables logically equivalent states to map to one another. So again, I would say consider your lab 1 where you did the fox, the feed, and the chicken problem. Did you use a specific ordering of a string, or did you actually implement a canonical form which would dramatically reduce the number of states you would specify in order to state what actions to do? Okay, that's much cleaner. Okay. Okay, so how do we measure problem solving performance? Before we get into the specifics of it, I'm just going to. So how do we design? How do we decide what criteria we need to consider when we want to evaluate the algorithm performance? Typically, we look at the following 4 criteria, which are completeness, optimality, time complexity, space complexity. Okay? Completeness, is our algorithm guaranteed to find a solution when there is one? Optimality, are we finding the optimal solution as opposed to a second best or third rate? Time complexity, how long does it take? And space complexity, how much memory is needed to perform the search? Okay? So we've come across some of these terms before in relation to identifying our task environment, and they are critical in evaluating the performance of search approaches. So time and space complexity are always considered with respect to some measure of the problem difficulty. Okay, they correlate with that. So we typically say the state space graph is the absolute value of the vertices or nodes and edges of the links between those nodes. So like this is naturally appropriate when we have a graph-based representation or data structure for our search problem. Again, our example of the map of Romania would be an instance of this. So in artificial intelligence, our graph is often represented implicitly by the initial state, actions, and transition model, but it is also often infinite. So when we're trying to represent the complexity, we typically represent it in terms of three quantities. Okay, so we have B, which is the branching factor, so the number of successors of any nodes, basically how many children does a node have. D, the depth of the shallowest goal node, so the number of steps along the path from the root, and N, the maximum length of any path in the state space. Okay? And time is often measured in terms of the number of nodes generated during the search, and space in terms of the maximum number of nodes stored in memory. So like typically we describe time and space complexity for search on a tree. So like we ask questions such as how redundant the path and the state space are, in assessing its effectiveness, we have to consider just the search cost, okay? So the time complexity. But including the term for memory usage gives us a better overall total cost because it's combining the both. Now, again, this is kind of counterintuitive in one sense because when you're taking a practical sense, we're looking at the problem from finding a route to go from Arid to Bucharest. So the search cost is the amount of time taken by the search, and the solution cost is the total length of the cost in kilometers. Okay? So in having the total cost, you're comparing milliseconds from the search cost, and you're comparing kilometers from the path cost, okay, which are two different what's the word? Two different quantities, values, because we have to add milliseconds and kilometers. So when comparing the two, it might be like pertinent to say something like what speed are we traveling at such that we can evaluate the performance of the search solution, that it gives us the step to take in a meaningful amount of time. Okay? But again, we'll cover more problems of that at a future date. Okay, so uninformed search strategies. What we're talking about here is search strategies that have no additional information about states beyond that provided in the problem definition. All they can do is generate successors and distinguish a goal state from a non-goal state. All search strategies are distinguished by the order in which nodes are expanded. And what we're going to cover is breadth first search, uniform cost search, depth first search, depth limited search, iterative deepening, depth first search, and bidirectional search. And again, one typically follows on from the other. So you'll see how each one introduces a particular limitation or is good in one particular case and not another. And the successor will have a variant approach that may address that concern. Okay. So breadth first search. Okay. This is an instance of the general graph search algorithm in which the shallowest unexpanded node is chosen for expansion. Okay, so the root node is expanded first, then all the successors of the root node are expanded next, then their successors, and so on. In general, all the nodes are expanded at a given depth in the search tree before any nodes at the next level are expanded. It's a general graph search, shallowest unexpanded node chosen, and it uses a FIFO queue for the frontier. Okay, so we'll have a look at this code. So the breadth for search takes in the problem description, returns a solution or failure. Node, a node with state, equals problem, initial state, path cost 0. So we have our node, which is our root node. If problem, goal.test, node.state, then return solution. So if the root node is the solution, then return it. Frontier is a FIFO queue with node as the only element. And again, like, okay, so if our root node was the goal node, we would exit this point and we would never continue on to the next line. So our frontier would never be defined. Otherwise, we define our frontier as a first in, first out queue with node as the only element. And our explored set is empty at present. Then loop 2, if empty, return failure. If frontier is empty, then return failure. It's not empty, we have our root node. Node pop frontier, so we take our root node from the frontier and we add it to the explored, and then for each action in problem dot action node.state do. Okay, so for each action, and again, what does our action refer to in the context of the tree search? It's every link connecting us to another node. So child is assigned child node, problem node action. Because it's deterministic and an environment, we know what doing that action to that particular node would be, so we are able to define our children node, our child node, and then we say if the child.state is not in explored or frontier, then okay, so if this child has not been explored previously or is not in the frontier, then we test the child node to see if it's the goal test. If it is, we would return and we would exit the program. Otherwise, we insert the child node in the frontier. And so on and so forth. Now that is added to the FIFO queue, and that will be investigated subsequently. This will loop around, and each node will be investigated on a depth-by-depth basis. Okay? Okay, so I guess there's one variant on the general graph search algorithm in this description, and that is the goal test is applied to each node when it is generated rather than when it is selected for expansion. So that's this guy here, okay? And that, we'll explain that later, but it's just to do with the memory requirements of the actual approach, okay? And relation to time complexity, okay? Additionally, we discard any paths to a state that's already in the frontier or the explored set, so we're not exploring within the paths. So as such, breadth first search always has the shallowest path to every node on the frontier. Okay. So what can we say about breadth first search? Well, we can say it's complete if the shallowest goal node is at some finite depth d. Breadth first search will eventually find it after generating all shallower nodes. And this assumes that the branching factor is finite, as in there's not a node with an infinite number of children. So as soon as the goal node is generated, we know that it is the shallowest goal node because all shallower nodes must have been generated already and failed the goal test. So the shallowest goal node is not necessarily the optimal one. Like, why is that? That's typically to do with the path cost. So, however, breadth first search would be optimal if the path cost is a non-decreasing function of the depth of the node. So the most common scenario where that would take place is where all actions have the exact same cost. Okay? In relation to time complexity, so if we imagine searching a uniform tree where every state has b successors, so it's the same number of child nodes, we would say that the time complexity would be b plus b to the 2 plus b to the 3 plus b to the 4. So that should be big O b to the d. There's a mistake there. Okay? So, in terms of space complexity, well, okay. So I guess I can change that. The reason it's b to the d, okay. If we were to apply the goal test to nodes when they're selected for actual expansion rather than when they're generated, that would actually be just slightly worse. It would be big O of b to the d plus 1. So we have to go one layer deeper before we'll expand the entire layer before evaluating is this a goal node. Okay? And that can dramatically increase the time complexity. So just keep in mind. Space complexity, any kind of graph search which stores every expanded node in the explored set. Space complexity is always within a factor of b, okay, of the time complexity. For breadth first graph search in particular, every node generated remains in memory. So there will be big O b to the d minus 1 nodes in the explored set and big O b to the d nodes in the frontier. Okay. Okay. And again, enjoy its operation then. So add A to the frontier, expand A, add B to the frontier, and C. Is B a goal node? No, it's not. Go on. Is C a goal node? No, it's not. Go on, expand B. Then we add D. Is D a goal node? No, it's not. Add to the frontier. Is E a goal node? No, it's not. Okay. Where's our next shallowest node to expand? It's back up to C because we're using FIFO, so the first in, first out. And C was an early part of the queue, so that's a shallower level than D and E. Okay? In terms of performance, okay, so exponential complexity bound is a problem. If we look at the following table, we assume a branch factor of b equals 10, that 1 million nodes can be generated per second, and that a node requires 1,000 bytes of storage. So we see that as the depth increases, the number of nodes is increasing exponentially. The time it takes to actually find a search solution is increasing exponentially, and the memory requirements for storing our explored set and our frontier nodes is just ridiculous as well. So the memory requirements are a bigger problem for breadth first search than its execution time. So the capacity to store this much data makes it intractable. Now, time is still a major factor. So typically, exponential complexity search problems can't be solved by uninformed search algorithms for anything but the smallest instances. Now, when we say small instances, like so, you know, when we know the depth is going to be below a certain level, okay, and it's kind of guaranteeable. But quite often we're dealing with graphs that have potentially an infinite depth level. We don't know where we're going to find the goal state, so that can't be decided ahead of time, which limits our application of these. Okay? Now, second one, uniform cost search. So instead of expanding the shallowest node, uniform cost search expands the node n with the lowest path cost g of n. This is done by storing the frontier as a priority queue ordered by g. Goal test is applied to a node when it is selected for expansion rather than when it is first generated. The reason is that the first goal node that is generated may be on a suboptimal path. The second difference is that a test is added in case a better path is found to a node currently on the frontier. So UCS takes in a problem, returns solution failure. Again, our root node is the node state, the initial state, path cost is 0. Frontier, we're defining our priority queue. And the priority queue is ordered by the path cost with the node as the only element. Explored is our empty set. So if empty frontier, return failure. But because we have our root node in at the moment, then it is not a failure. Node pop frontier, so it chooses our lowest cost. We only have one, so we pick it. If problem goal test, node.state, return solution. It's not our solution, we don't return. Add node.state to explored. So now we know what arid is or whatever. For each action in problem action, node.state, again our actions include our links between arid to the other cities. So we define child nodes to our frontier on that basis. Well, first we generate the child node, then we check to ensure that it's not in the explored set of the frontier already. Then we add it to the frontier. Okay? Else if child stayed in frontier with higher path cost, then replace that frontier node with child. Else if child.state is in frontier with higher path cost, then replace that frontier node with child. So if we already have the resultant state, which is the city we would end up at, should we follow this child node, and if it's already in the frontier, then we replace it, okay? Because we've already explored it essentially. So that goes around, it adds our 3 nodes to the set, and then the next time we come around, and we'll say, where do we get the cost? Node.pop frontier, okay, so we choose, okay, so our child, when it's being added, remember what the summation of the cost will be the cost of the parent node, which in the case of arid would be 0, plus the cost to the current node. So whatever, for whatever that is, we'll then select the child with the lowest cost as the next node to expand. Okay? Okay. And again, so if we say that when all step costs are equal, breadth first search is optimal because it only spans the shallowest unexpanded node. So we're talking about breadth first search there. So by extension, we can find an algorithm that is optimal with any step cost function. Instead of exploring the shallowest cost of the shallowest node, uniform cost expands based on the node with lowest path cost. And again, that's down to our ordering function and combining it with the priority queue. Okay, So if we take an example of this, we'll have a look at uniform cost search. We want to see that whenever it selects a node for n for expansion, the optimal path that node has been found. Where it's not the case, there will have to be another function, node n, on the optimal path from the start node to n by the graph separation property. Okay. So if we want to get from Cebu to Bucharest, successors of Cebu are Ramuku Vuke and Fagaris. Okay, so if we're going for the cheapest, then this guy is our cheapest. So we expand Ramuku, and this would add Petesti to the frontier. But notice how Petesti has the sum of the pad cost as the cost associated with it, while Fagras has the cost of 99. Okay, so the least cost node is now Fagras, so it's expanded, adding Bucharest with a cost of 99 plus 211, which equals 310. Okay, so now a goal node has been generated, but uniform cost search keeps going, choosing Petesti for expansion and adding a second path to Bucharest with an overall cheaper cost. So now the algorithm checks to see if this new path is better than the old one. It is, so the old one is discarded. Bucharest now goes with a cost of 278. It's selected for expansion, and the solution is returned. Okay? Now, depth first search. So depth first search expands the deepest node in the current frontier of the search tree. The search proceeds immediately to the deepest level of the search tree, where the node has no successors. As those nodes are expanded, they are dropped from the frontier, so then the search backs up to the next deepest node that still has unexplored successors. So again, it's like a variant of breadth first, where rather than going for the shallowest node, we're going for the deepest node. Now, it also differs in that instead of using a FIFO queue to implement this, depth first search uses a last in first out queue. Okay, and there's two versions. There is graph search or tree search version, and we can see its operation here. So again, we have A adds the frontier, doesn't suit the goal, expand it. So now A adds B and C. So B is now the deepest node on the frontier based on our last in, first out. So we'll choose this guy for expansion. So now that we've expanded B, E, and D have been added to the frontier. So that was the last guy to be added, so we expand him. And now we have I and H have been added to the frontier. Expand H. Now, there's no deeper layers to expand to, so we can discard H at this point, as we see here, and we hop back over to I, and then there is no successive states to I, and we haven't achieved the goal state, so we discard that. So we jump back up to E, and again, E has successors, so we go to the deepest one there, which is the last one to be added, which was J. So J has no successors, not the goal, discard, so on and so forth, until we arrive at whatever our goal node is. Okay? So N, in this instance, is our goal node. Okay? Now, what the LIFO queue means is that the most recently generated node is chosen for expansion. This has to be the deepest unexpanded node because it's one deeper than the parent, which in turn was the deepest unexpanded node when it was selected. Okay, now this can be implemented with graph search, but as an alternative, you can implement depth first search with a recursive function using tree search. Okay, that calls itself on each of its children in turn. Okay? In terms of the property of depth first search, it really will depend on whether the graph search or tree search version is used. The graph search version will avoid repeated states and redundant paths. It's complete in finite finite state spaces because it will eventually expand every node. The tree search version, on the other hand, is not complete because the depth first tree search can be modified. Oh, okay, so depth first tree search can be modified at no extra memory cost so that it checks new states against those in the path from the root to the current node. This will avoid the infinite loops in finite states, but does not avoid the issue of redundant paths. In infinite state spaces, both versions fail if an infinite non-goal path is encountered. Okay? Both versions are non-optimal. So like depth first search would ignore the entire left subtree if C is a goal node. So if C was a goal node, which means that like we can go on exploring this infinite tree or subtree that does not contain a goal node, and we never arrived at. Okay. Okay. So just to finish up on that. So the time complexity of depth first search, it's bounded by the size of the state space. Again, this can be infinite, so a depth first tree search. You can generate, big O of B, which is the branching factor, to m to the power of m, where m is the maximum depth of the node, because it doesn't necessarily have to find the goal node. Okay? And again, m can be significantly deeper than D, where D is our shallowest goal node. Again, consider the example where C is our goal. We're going to go right down to M, which is the deepest level we explore. And if it's infinite, we'll basically go until we run out of memory. Okay? But we'll never arrive at the goal node desired. Okay? Which will be D. So in that case, D will be 1, M is infinity. Okay? So there's not many clear advantages over breadth first search, so why do we bother including it? One advantage it has is space complexity. For a graph search, there's no advantage, but a depth first tree search only has to store a single path from the root to the leaf node, along with the remaining unexpanded siblings, for sibling nodes for each node in the path. So that one variant will provide us with gains in terms of memory required. Okay? While the graph search version would not. Once a node has been explored, it can be removed from memory as soon as all its descendants have been fully explored. Okay. Okay. Again, there's variants in this approach, which I'm not going to go into today, but I might get to next week. So depth limited search. Okay, so the failure of depth first search in infinite state spaces can be alleviated by supplying depth first search with a predetermined depth limit L. That is, nodes at depth L are treated as if they have no successors. Okay, so the depth limit solves our issue with the infinite path problem. But then we can add other sources of incompleteness. So if we choose a limit that is lower than depth D, where D is the shallowest goal node we're looking for. Okay? That introduces the problem because the shallowest goal node will be beyond the depth limit. And again, this is unlikely when we don't know D, the depth of the shallowest goal node. Okay? In the case where L is greater than D, it's also suboptimal. And this is due to time complexity, where it would be, so the space complexity would be, the time complexity would be big O to the big O of the B, and the space complexity is big O of the B. Okay? But again, depth first search can be viewed as a particular instance of that problem, with depth limited search having, time complexity is big O to the power of L. Okay? Big O of B to the power of L. Space complexity is the big O of BL. Again, this is for the aforementioned reasons. Okay? And depth first search can be viewed as a special case of depth limited search where L is equal to infinity. So the prior approach is the exact same as depth first limited search where we specify a limit of infinity. Okay? And again, these implementations are almost identical. So depth limited search takes in the problem and the limit. Return a solution, failure, cutoff. Return recursive, depth limited search, make node, problem, not initial state, problem, comma, limit. So you're making a recursive call. This will continually recall the same problem, just one node further along the approach. As such, you generate a recursive call that will reduce us to the base case being arriving at our goal state. When that eventually returns, the returns will percolate the whole way up, and this is why we're able to achieve the space complexity of big O BL. Okay? I hope that makes sense. Other than that, it's very similar. We're taking the node, problem, limit. It's a problem that goal test, node state, then return solution node. So that'll be base case passed, success. Else, if limit equals 0, then return cutoff. So our limit will be decremented each time. And when we reach 0, then we know that we've reached our depth limit and we should return cutoff or failure. Else, cutoff occurred equals false for each action in problem action node.state do child node problem node action. So define what our child node is and invoke an instance of recursive depth limited search with that child node, the same problem, and the limit decremented by 1. If result equals cutoff, then cutoff assigned true. So this again is this is allowed the percolation to know that the call to the recursive function has returned the base call. Else, if result is not equal to failure, then return result. If cutoff occurred, then return cutoff, else return failure. So eventually, when we get to okay, there's a couple of things to think about here. Okay, eventually a cutoff will occur. That cutoff will mean that we've reached the depth level we're allowed to go. Okay, in which case we should ignore that tree and go to the next subtree that has not been explored to that depth as of yet, which is why we're returning cutoff as opposed to failure. That's why it's cutoff and failure are distinct. Okay? So when is failure returned? Okay? Failure is only after occurring when we have searched, when the cutoff has occurred is true, and that only occurs when our limit is equal to 0. Okay? So we're going down to our maximum limit, our maximum limit, our maximum limit, then our next maximum limit, then our next maximum limit across all the nodes. So do we increment above 1 or do we not? Okay, which makes sense. Okay. What I was thinking was kind of, I'm trying to picture the operation of it in my head, and just so you're clear, what I'm thinking is it pops down. So in search is this entire way down, okay, and then entire way down as far as the depth limit allows. So that's just to make it tractable, okay, okay, which is fine. I'm just kind of curious in my head now what a variant of, well, I suppose the opposite variant of that will be breadth first search, where we're searching everything sequentially. Okay, okay, that's fine. Okay, so like again, there are some issues with this where like depth limits can be based on the knowledge of the problem. So we don't always know what D is going to be, and we don't always know what L could be. So like in the Romania problem, there are 20 cities. So what should the L be in that instance? What's the limit for that? Okay, so the longest potential path is 19 if we have 20 states. Okay, but if you look at the map, you'll see that you can reach any other particular city from the one we're currently in at most 9 steps. So like this number, it's referred to as the diameter of the state space, and that gives us a better depth limit, which will be a more efficient depth limited search, which all sounds great. But the problem is you won't know the depth limit until you've solved the problem. Okay, so it's not much good to you ahead of time. Okay. Um, okay. So that's kind of limitation of that. Okay, so now iterative deepening search is a general strategy often used in combination with depth first tree search that finds the best depth limit. It does this by gradually increasing the limit, first 0, then 1, then 2, and so on until a goal is found. Okay, so rather than specifying an ultimate depth, like in depth limited search, what we do here is we do an iterative deepening depth first search, which is we're going down the trees gradually. Okay, and then we're increasing the limit as each limit is reached, which is kind of the solution I was thinking of in the back of my head. Okay, and it makes sense. Okay, so like this occurs when the depth limit reaches D, the depth of the shallowest goal node, and the benefits of this is that like iterative deepening combines the benefits of depth first search and breadth first search. Like depth first search, its memory requirements are modest at big O B of D. And like breadth first search, it's complete. And when the branching factor is finite, that we're going to search across all the individual nodes when the path is a non-decreasing function of the depth of the node. Okay? So is it wasteful? Total number of nodes in the worst case. So again, like we are like at level 1, we're searching all these nodes. But with level 2, we're going to rehash and redo all these nodes. And at level 3, we're going to rehash all these nodes and so on. Okay, so in that sense, iterative deepening search may seem wasteful because the state's generated multiple times, but realistically, it's not too costly. Okay, the reason that is that in the search tree with a similar or very similar branching factor, okay, at each level, most of the nodes are in the bottom level. Okay, as in like it's if each level of the tree is expanding by a branching factor of 3, then clearly the lower levels will have the highest number of nodes. Okay, so it doesn't really matter that the upper levels are generated multiple times because they are a kind of a fraction of what those below them will be. Okay, in the iterative deepening search, the nodes at the bottom level are only generated once. Like those in the next to bottom level are generated twice, and so on and so forth. Okay, up to the chin of the node. So in that case, like your worst case scenario for the number of nodes is big O of number of nodes if you can search is D, so the shiniest goal node times the branching factor plus D minus 1 times the branching factor to the power 2 plus up to 1 times the branching factor to the power of D. Okay, so these numbers get smaller as the level is decreasing. Okay, or sorry, the way around. Okay, it's just basically saying that the initial layers are not as big a concern. Okay, and this gives us an overall time complexity of big O of b to the d, which is kind of the same as breadth first search. Um, there's more cost for generating the upper levels multiple times, but it's not massive. Okay, so again, if you take the example of where the branching factor is 10, depth is 5, these are the kind of numbers you're looking at for the two approaches, 120,000 as opposed to 111,000. Okay, now bidirectional search. Okay, this is our final one for today. So this is two simultaneous searches, one forward from the initial state and the other backward from the goal. And we hope that the two searches will meet in the middle. The motivation is that the, the branching factor to the power of the depth divided by 2 plus the branching factor to the power of the depth divided by 2 is much less than the branching factor to the power of the depth. Our D, where the D is the lowest, the shallowest goal node. Okay? So the area of the two small circles is less than the area of the one big circle centered on the start and reaching to the end. Okay? That's the idea. So it's implemented by replacing the goal test with a check to see whether the frontiers of the two searches intersect. If they do, a goal has been found. So again, you're expanding from the goal and you're expanding from the starting point. And you're seeing, do our frontiers match? If they do, then it's a benefit. Okay? Now again, just consider that when you find the first solution, it may not be optimal. Okay, so even if both searches are breadth first search, some additional search is required to make sure there isn't another shortcut across that gap. And the check can be done when each node is generated or selected for expansion. And if you use a hash table for this, it will take constant time in looking it up. Okay. Now, I suppose the benefits of this approach is like it provides a reduction in time complexity, and that makes bidirectional search attractive. But the issues with searching backwards can prove difficult. Okay, like it can be so complex that it doesn't warrant the actual effort it requires. Okay, so like if you're to say that the predecessors of a state X
be all those states the X have as a successor. Like, bidirectional search requires a method for working out those predecessors. And when all the actions in state space are reversible, the predecessors of X are its successors. So that could require a bit of thinking in terms of figuring it out. Okay, which is one drawback of it. Okay, so I'm kind of going over the 2 hours mark there now, so I have to finish up. But again, this is just a comparison for the tree search versions of these graphs. For graph searches, the main differences are that depth first search is complete for finite state spaces, and space and time complexities are bounded by the size of the state space. So what do we have? Breadth first search complete? Yes. Time, big O b to the d. Space, big O b to the d. Optimal? Yes. And again, there's a couple of caveats listed down here, such as if the world state is finite, if it's not finite, if it's infinite, whatever. Okay? I'm going to leave you go through them because I'm out of time and I have to go to something. So thanks for listening. I'll post this up on the YouTube channel and then I will link it. And apologies for forgetting to record the Zoom lecture and the delay in getting this material to you. Take care.